Everyone. In the morning, we looked at basic cluster usage and how to submit a job, etc. In this session, we are going to look at more from the parallel job submission perspective. And Dr. Nikhil is going to talk to us about all these various aspects of parallel programming, etc. So over to you, Nikhil.
And is my screen visible?
Yes.
So I'm unable to hear Rupesh's voice clearly. Is it a problem on my end? Or I don't know.
Is anybody else able to hear? Yeah, Nikhil, you are audible.
Okay.
Yeah, Nikhil, you are audible.
Okay. So, well, I'll start. Welcome back, everyone. And so, as Rupesh mentioned, the morning session was mainly about how we use clusters. And in that process, we saw that none of the programs that we used were written in a parallel programming language. In this session, we will look at the basics of parallel programming. So different programming models, programming paradigms, and as part of hands-on, we will also write parallel programs and use those programs in the jobs that we submit to the cluster. So how are clusters programmed? So clusters have massive amount of hardware parallelism. So recall that they have these lot of green dots, which are nothing but independent computers. And we need to execute a program on these multiple computers. And processes and threads are units of execution. So many people get confused with processes and threads. So let's get that cleared straight away. So these are abstraction provided by the operating system. So a process is self-contained. It has its own private resources to execute programs. An example of a resource is memory. And a process is also an instance of a running program. If the programmer has an illusion that the entire computer is for himself or herself. So when a programmer is running a process, so he gets an illusion that the entire computer is for himself. And whereas a thread, it always belongs to a process. It shares the memory and other resources that the process has already acquired. And it shares these resources with other threads if they exist, and the threads that are part of the same process. And the thread gets an illusion that the entire processor or core is for itself. A thread can also be considered as a subroutine in the main program. So cluster programming is mainly about exploiting parallelism. And we have sequential programs, so the most basic or simple type of programs. So you have a single sequence of instructions that are being executed. You have a problem. That problem is broken down into a sequence of instructions. And these instructions go through the processor. You have a single core. These instructions are processed one after another by this core. So that is the model in which sequential program works. Now you have concurrent programs. So in concurrent programs, there are multiple sequences of instructions, and all these sequences are executing concurrently, simultaneously. And the instructions from one sequence may communicate and interfere with others. So depending upon how these multiple threads, which are processing these sequence of instructions, are executing, we can have various flavors of a concurrent program. Any question? Okay. So, and these flavors are, so we can have multi-programming, where multiple threads, they multiplex their execution on one processor or one core. You can have multi-processing, where multiple threads of a program, they multiplex their execution on multiple cores. And then you can have distributed processing, where multiple processes, they multiplex their executions on multiple nodes. So we are familiar with the notion of nodes, cores, and processors. So core and processor was used interchangeably when we were writing job scripts, but in hardware, a processor might have multiple cores. So that was what we learned this morning. So one other term that we often get to hear is that of a parallel program. So a parallel program is basically a concurrent program designed to run on parallel hardware. So, and multiprocessing and distributed processing is their examples of parallel program. Okay. So you have a problem, you break that into multiple sequences of instructions. Each sequence goes into a separate core or processor. So that is shown in this picture. Okay, so we talked about a parallel program as something that is executing on parallel hardware. Now, what kind of parallel hardware exists out there? So Flynn's taxonomy is very popular and it categorizes the computing system based on how the processing elements see instruction and data. So if you have single instruction stream and single data stream, it is SISD. If you have single instruction stream and multiple data stream, then it is SIMD. If you have multiple instruction stream and single data stream, it is MISD. And if you have multiple instructions and data streams, then it is MIRD. So I will, okay, before I talk about the details of each of these, please note that clusters belong to the MIMD category. So multiple instructions and multiple data streams. So I will talk about only the most popular ones and the ones that were popular earlier. So SISD was popular when we did not have multiple core machines. So you have a single stream of instructions and single stream of data. And you have block A, block B, and you're supposed to add the elements of block A with elements of block B and store the result in a block C. So I've shown the breakup of these blocks A and B. Now in SIMD machine, so in every cycle, we have the same instruction being executed by all the cores that exist. So we have 3 cores in this example. So each core executes the same instruction load, but it is operating on different data. So core 1 is operating on A of 0, while core 2 operates on A of 1, and core 3 operates on A of 2. And in cycle 1, a different piece of data is loaded. And in cycle 2, you operate on already loaded data. Each core does the same operation, but is operating on different piece of data. And lastly, in cycle 3, you store the result back. And that's how you get the result computed in log C. So this is an example of SIMD machine. So it happens in lockstep fashion. So every cycle, same instruction, but different piece of data. So all cores here are executing the same instruction in the clock cycle, but they're operating on different data. Examples of such machines are GPUs. And modern CPUs, they also have these SIMD subcomponents. What it means that these multi-core machines, they might have instructions, like vector instructions, that allow you to do something like this. Okay, so the other type of parallel hardware is MIMD, and clusters belong to this category. Every core piece of data. So that is multiple instruction, multiple data. The cores may or may not go lockstep, as we saw in the previous example. And which also means, so the other term is synchronous or asynchronous. Examples of these type of machines are clusters, supercomputers, and multi-core machines. So just like we have CPUs, or even, so I mentioned this earlier in the previous slide. So MIMD computers can have SIMD subcomponents. So multi-core PCs that we see today, they can have SIMD components. So there's also another way of categorizing systems based on how processing elements see the system memory. So this is also based on, so in other words, you can look at how the memory is architected and come up with this categorization of parallel hardware. Okay. So I just noticed a question on the difference between clusters and supercomputers. So in clusters, so as I mentioned this morning, so supercomputers can be thought of as specialized clusters. So in supercomputers, you have, they say, tight coupling in terms of, let's say, a particular application, say weather prediction, is run on a supercomputer, and that is the only application that is run. Then the cabling that you use in order to interconnect computers, that might be specific. So we might not need a topology like Torus. It might be something which is very customized. The operating system might be very customized. Okay. So in our cluster, we have various flavors of Linux. So CentOS, Red Hat Linux, Ubuntu, and so on. But in supercomputers, it might be a very lightweight operating system or even customized. So that is the difference. Okay, back to our categorization of parallel hardware. We can have shared memory, distributed memory, and hybrid of distributed shared memory. And clusters, most of them, they belong to this hybrid category, distributed shared memory. Now, in shared memory architecture, you have a piece of memory that is accessible by all the processors in a uniform fashion. So take that with a pinch of salt. So when I say in a uniform way, you can also have non-uniform memory access, and that is also part of shared memory architecture. But the common ones we have are these where memory is visible to all the processors in a uniform way. And in distributed memory architecture, you have multiple processors, and each processor has its own private memory. And these processors are connected to each other with the help of an interconnect. I think my share just went off. Is it back?
Yeah, it is visible.
Yes. Yes.
Okay. Okay. So yeah. So in distributed memory architectures, you have each processor having its own private memory. And So talking about parallelism, concurrency is the basis for writing parallel programs. And we can have different parallel programs such as threads program. So you can have a C or C++ threads program. So P threads program, OpenMP program, Mpi program, and so on. So you will learn that more in a detailed session on this parallel programming next week. So you'll learn about these different programming models. And two common types of programming parallel programming patterns are data parallel and control or task parallel. And so in data parallelism, threads execute the same function, but with different data. So an example or an analogy would be two construction workers. They are doing the same function of laying bricks, but they are doing it at different parts of the house. So that is an example of data parallelism. Now, an example or an analogy for control parallelism is while a carpenter is getting a window frame ready, a mason is laying bricks in the wall. So they're doing different functions at the same time. So that is an example of control or task parallelism. Now, OpenMP is a popular programming model for writing parallel programs. And it's an open standard for writing shared memory parallel programs in C, C++, and Fortran. And now, with the latest flavor of OpenMP, you can also write C, C++ programs and run those programs on GPUs. And Professor Unnikrishnan will talk about that in the next week's session. OpenMP is supported by IBM, Intel, GNU, and others. And here, the same program is running on multiple threads. Each thread is operating on different data. So you have single program, but operating with multiple data. So you have SPMD model. So why do we need OpenMP? Any question?
Yeah, so I just would like to know, Nikhil, what is the difference here when we are considering multiple processors and multiple thread? I mean, on the same system, we can have, as you just said, one processor can have many CPUs, is what you told. So what will be the difference when we are running the OpenMP on threads versus cores?
Okay, so OpenMP program always, we work with threads when we are writing OpenMP programs. And those threads are having an illusion that they have a single core, entire core for themselves.
Okay.
So these threads are all part of one process.
Okay.
Okay, so why do we need OpenMP? So OpenMP allows a program to scale seamlessly and automatically. So which means that your program is running on, let's say, 8 cores. Now you change the hardware, you make it more powerful, and you add few more cores. Now you have 16 cores. You can run the same program, okay, and that program will utilize all the 16 cores that are available. So that is seamless utilization of the increased availability of parallel hardware. So with earlier programming models such as P threads, that was not possible. If the number of cores changed, then you had to create more number of threads so that each thread could run on those cores. Yeah, so we say OpenMP provides a scalable and portable alternative to data parallel computing on shared memory architectures. Okay, so how does programming in OpenMP look like? So as I mentioned in the previous slide, its OpenMP program is basically a C, C++ or Fortran program. So you have let's consider C program. So you have a C program with what are called as compiler directives, which look like this #pragma Mpi parallel. So and #pragma 134. These directives are stuck in between the program. And the meaning of hash pragma parallel is that it executes as many threads as there are processors. And hash pragma Mpi4, it divides the whole work among available threads. So the whole work here means that there are n iterations, and those n iterations are divided among the available threads. Okay, so this example of the hash pragma with OpenMP, it's an example of loop parallelism. And this kind of parallelism is very common in scientific codes. And OpenMP also supports the other forms of parallelism, but it is known for writing programs which have this loop parallelism. And one detail that I did not mention is that what happens when there are data races. So what is a data race? I will explain that in a couple of slides from now with the help of an example. So let's consider, let's look at this animation of how this hash pragma OMP parallel works. So initially, execution begins with the master thread. You just have one thread of execution. And let's say that thread is executing a sequence of instructions which belong to code region 0. Now, this master thread creates or forks worker threads. So how many worker threads? It depends on the number of cores that are available. And now all these worker threads, they start executing the sequence of instruction that belong to code region 1. Next, you have hash pragma Mpi4 followed by a loop body. Now, the same set of workers, they all begin to execute code region 2. And before they do that, there is something called as a barrier or a synchronization point. So they all wait at that point. So different threads might take different time to execute the sequence of instructions in code region 1. And because of that, they might reach this synchronization point, the black horizontal line that you see here in this picture. So they might reach that line at different points in time. So the barrier ensures that when they start executing code region 2, they all do at the same time. So next, after executing code region 2, when the for loop body, they exit the for loop body, they all begin to execute code region 3 at the same time. Again, there is a barrier that is inserted. So these barriers, they are implicit barriers. The programmer doesn't get to see them. They exist because of hash pragma Mpi4 and hash pragma Mpi parallel. But there are explicit barriers as well supported in OpenMP. And if a programmer wants to explicitly introduce these synchronization points, he or she can do so. So lastly, when the workers are done executing code region 3, they all join master thread, and there is just one thread now that starts executing code region 4. Okay. So the workers, they exist at a small code snippet, which is enclosed in this hash pragma Mpi parallel structure. And outside this block, the workers don't exist. So this is in contrast to, say, thread-based programming, where once you create a thread, until you destroy that thread, the thread continues to exist. And also in MPI, as we will see in the next few minutes from now. All right, so we saw that execution begins with a master thread. The master thread creates or forks worker threads. And worker threads, they join the master thread after they are done with executing their work. This is called as fork join parallelism. Now, how many workers or threads are there? So as I mentioned, depends on the number of cores that are there. We can also set this parameter with the help of an API provided by OpenMP. So it's OpenMP set num threads. You can query the number of processors that are available with the help of OMP get num procs. You can also get the ID of a thread with the help of OMP get thread num. So I'm introducing you to the minimal stuff of OpenMP, and detailed OpenMP programming will be handled by Professor Krishnan in day 2 of the workshop. Okay. So let's consider an example of summing array elements. So you have an array A0 to A9, and now I divide A0 to A9 into 2 smaller subblocks, A0 to A4 and A5 to A9. And let's say I have 2 workers or 2 threads in my program. I assign one work, summing A0 to A4 to worker 1, summing A5 to A9 to worker 2. And once these workers, they finish summing, and they add the sum, their respective sums, to the variable called sum, which is created by the master. And in the end, you have master seeing the correct value of sum. But does master really see the correct value of sum? It depends, because sum is shared among workers. Only one worker should be updating sum at a time. So we say that there's a data race. It happens because one of the threads is trying to write, or in this case, both the threads are trying to write, and there is no controlled access to those writes. So that is a data race. And here is another example. You have 2 ATMs, and you're trying to withdraw some money from the ATM. If the balance is 10 and you're trying to withdraw amount 8, the check at ATM 1 goes through. And the check at ATM 2 also goes through if the sequence is as shown here. Now, at both the ATMs, the check has passed. And after updating the balance is 2 now at ATM. Now at ATM 2, the balance is minus 6, because you're trying to withdraw 8 and the balance is 2. So balance becomes minus 6. And this is clearly something that we do not want. So there is again a data race here. And there is something more than that. So we should not allow multiple workers to execute this code region within the if body. So we call that body of if as a critical section. So in a sequential program, you have a total ordering of the instructions. So one instruction follows another. So there's a total order. But in a parallel program, that is not the case. And this leads to non-determinism in a parallel program. So with every run of a parallel program, the behavior might be different. Of course, the visible behavior might be the same. If you are trying to print something, so that is visible behavior. So that might be the same and as expected, but the exact sequence of instructions that are executed, that changes with every run. And in modern computer architectures, so one example, you have this hyper-threading. Because of that, you can have a non-determinism even in sequential programs. So in order to coordinate access to shared variables, you need to synchronize. You need to introduce synchronization among threads. And the synchronization helps avoid race conditions. And coming back to our example of summing the array elements. So in the earlier example, the blocks were divided into two, and each worker summed, and they all were trying to write or update the shared variable. And in this example, master creates two separate variables, sum1 and sum2, and worker 1 just computes the result and puts in sum1. Worker 2 computes the result and puts it in sum2. And master then computes sum as sum1 plus sum2. So in this example, you don't have a race condition because each worker is working independently and is not sharing any variable with other thread or other worker. So this is, again, we have seen this kind of example. So this is an example of data parallelism. There is another feature, a very powerful feature in OpenMP called reductions. So you take something complex and reduce it to something simpler. And for example, array to scalar variable. So scalar meaning just a single unbreakable type. So you have an array to begin with, and you take adjacent pairs. So let's say we are trying to sum the array elements in parallel. So the adjacent elements are considered, and they are summed in this level 1 of this inverted tree. And in level 2, you have partial sums computed again. And finally, in level 3, you have the final result. So reduction might not do this in an exact manner as shown here. Instead of adjacent pair of elements being added, it might take any two elements that are available as determined by the implementation. So an example of reductions. So here, sum is initialized to 0 by the master. So this is the same example where there was a shared variable sum. And the only difference is here that programmer doesn't need to serialize or synchronize access to sum. If you use the reduction keyword provided by OpenMP, then you can get the correct value of sum seen by the master. So here is an example program that uses reduction. So this is the same example, summing array elements. And in the first part of this in this program, so int I equals 0, I less than num samples, a of I is equal to I. So this is initializing the array elements. And then you have the hash pragma OMP parallel. Now you have a set of workers that are created. And then you have hash pragma OMP for reduction. And reducing on a variable called total. Total is nothing but the partial sums that are accumulated by each thread. So what happens here is that in the for loop, you can see that it runs from 0 to num samples. These iterations are broken down among different threads. And each thread or worker operates on only those iterations. So they accumulate partial sums and they add it to total. And no serialization to total, accessing total is necessary here. It is taken care of by the underlying type system. So there are more reduction operators that are available in OpenMP. So multiplication, bitwise OR, and XOR, logical OR, and AND. As you can see, these are all commutative in nature. So in summary, OpenMP provides a way to specify what parts of the program can execute in parallel with one another. So if you have a whole program, you can only specify a small part of the program as executing in parallel. And how the work is to be distributed across different cores. You can also specify that, but I didn't mention that in the previous slides. So you can also serialize access to memory. And atomic is one of the keywords that is available. So you can have hash pragma OMP critical and many other such constructs are available in OpenMP. So this happens while you get a portable. Now, so that was about OpenMP, and OpenMP was a shared memory programming model. So in shared memory, you have a piece of memory that is visible to all processors out there. Okay. And because of this, all processors or all worker threads, they were able to update that same shared variable sum. Okay. And because of that, we had problems of data races. In distributed memory programming, that problem is not there, but there are more problems here. Okay, so writing parallel programs, correct parallel programs is challenging. So distributed memory programming is it's a little more complicated than shared memory programming. So in this model of programming, a program executes as a collection of processes. So in the earlier case, it was threads. So you had multiple threads executing within a process. Now you have multiple processes. And all these processes together, they accomplish a task. So when we say process, each process has its own memory. And so the total memory that is available for an MPI program is the combined memory space of all processes. So there's a typo here. It should be all processes, not processor. So, and if one process has to exchange data with another process, then an explicit cooperation is needed. And here, for example, we have process P1 and process P2. And process P1 must explicitly send a message to process P2 saying that it wants to send some data. And process P2 must be ready to accept that data. So process P2 should be able to receive that data that is sent by P1. So programmer must explicitly set up communication channels between communicating processes and then exchange the data. So this is the picture that I shared earlier of a distributed memory programming model. So each processor has its own private memory. And if I declare a variable A, that variable A exists as separate copies in each of the process that is executed. And those are separate copies. Now, value of A in one copy might be different from the other copy. So if P1 sends a copy of A to P2, then P2 receives the copy, stores in its data region. Okay. So, and the reason why value of A might be different is because each processor has its own private memory, and there is no requirement that all these copies must be synchronized. And every data element, so every variable that you have, it must belong to one of the memory spaces. And it is programmer's responsibility to decide where to place that particular data. So if in this example, if processor 1 is executing, let's say, process 1, and process 1 doesn't ever use the variable A, then it is a waste of memory space to place A very close to process 1. So programmer must be aware of all such details in order to get the best out of distributed memory programming model. So that's why it is more complex than shared memory programming model. And these programs are written in SPMD, so single program, multiple data. But the biggest advantage that distributed memory programming brings is that the power and cost scaling is better than with shared memory. So you can have introduce millions of cores, and if a program is doing parallel work, then all the cores can be utilized, and you can get better performance as you keep on adding more and more cores. So the fastest supercomputer in top 500 has about 7 million cores. I think it's Fugaku, about 70 lakh cores. And so example applications are weather forecasting. And let's say we want to decide where to put exhaust fans in a basement parking. So can a tank topple while wading through a body of water? So these kind of decisions can be answered in a more in a better way when we do simulation of so in fluid dynamics. So here is an example of distributed memory programming model. So the problem is to compute the distance between blue dots and red dots. So for every blue dot, you have in the code, you have the outer for loop. For every blue dot, you pick a red dot, compute the distance between the blue dot and red dot. So you have the inner for loop. So inner for loop representing the red dot. And then you compute the distance. So distance P of I and R of J. So R of J represents the data for the red dots. P of I represents the data for the blue dots. So in distributed programming memory model, distributed memory programming model, you have first, let's say we have processes P1 and P2. Each process has the entire memory created for storing the results, T. So we can also optimize there. And let's say each process is given. Initially, only P1 has all the data. Now P1 sends R, the data block R, and B to P2. P1 breaks the data and sends it to P2. P2 receives the data. So it receives B and R. It computes the distances corresponding to the data that it received. And that means that P1 computes the results, or it populates the upper 4x4, half of 4x4 matrix, and P2 computes the lower half of 4x4 matrix. After P2 computes the results, it sends the computed results of the lower half of this 4x4 matrix D back to process P1. Now P1 receives the data, so and it has the complete picture of the computed results. So that's how processes P1 and P2 exchange messages and accomplish the task of computing the distances in parallel. Now, several questions exist here. So that animation is shown in code here. You have different data blocks, B, R, and D. Processor P1 sends B and R to process P2. Processor P2 receives B and R from process P1. So for every send, there must be a corresponding receive and vice versa. And then the actual work happens. So process 1 works on points 1, 2. So on blue points 1 and 2. Process 2 works on blue points 3 and 4. So, and then they compute the distance and the result is computed, and processor P1 gets the result back. So the questions that remain is, how do we know that this dividing the work, process P1 computes result 1 and 2 for the blue dots, and process P2 computes the distances with blue dots 3, 4. So how do we know that this is the best configuration? And how do we know that data that is sent from process P1 is actually received by the process P2? So what does it mean to send and receive complete? How do we know, or how does a receiver interpret the data that a sender sends? So it's just a sequence of bytes. How does a receiver interpret? So these questions, based on these questions, there are different APIs that are available in MPI. And the objective of this session is to not give you a detailed introduction about MPI programming, but to tell you that there is something like MPI, which is a distributed memory programming model. And using that, you can write programs that could run on millions of codes. So that is that. So when we are writing MPI programs, so we need to remember these things. So the first thing is about initialization and termination sequence. So this is an example of C or C++ program. So again, MPI programs can be written in C, C++, or Fortran. We can also have Python or MATLAB code translated to MPI, but we're not talking about that in this session. Okay, so the initialization sequence, the API that is available is Mpi init. So Mpi init accepts two arguments, so argc and argv, and they're prefixed with this ampersand. So ampersand is a notation in C, C++ programming to refer to a memory location. So they're technically called as pointers. So the address of named as argc. Which is Mpi finalize. So this Mpi finalize releases all system resources. Okay, so this is an Mpi program talking about initialization and termination sequence. Now you also have an Mpi environment. So you have ranks or process numbers. And in this example, in this picture, you have a logical grouping of process numbers 0 to 5. So 0 to 5, they all belong to one group, which is called as Mpi world. So it's also called as a communicator. And any process that belongs to a group can exchange messages with any other process that belongs to the same group. So you can create smaller subgroups. And Mpi init initializes this communicator. And what is this rank and size? So rank is basically the process ID, and size is the number of processes that are executing. So you have Mpi size, and that is an API provided by Mpi. Then you have Mpi rank. So these APIs, they fill in the variable size and rank respectively. So when I say they fill in, they provide as output values of these size and rank. If you are running your Mpi program with 10 processes, and when this line is executed, Mpi size, so at the end of execution of this line, then the size variable will be 10. If you are after execution of this Mpi rank, there will be, if you are running with 10 processes, each process will have its own value of the rank populated here. Now, so we saw initialization and termination sequence. We saw what is size and a rank. Now it's the time to do actual work. So we have some work. We need to divide that work among existing processes. And in OpenMP, if you recall, we had to sum the array of 10 elements. We divided those 10 elements into two chunks. One worker thread was doing 0 to 4, the other worker thread was doing 5 to 9. Now, you can do something smarter, and you can use these values of rank and size to distribute these data blocks among available processes. So that for loop that is shown here, for I is equal to rank star num points divided by size and so on, that basically distributes a data block among different processes that are being used. Now, once you have divided the work, each process does its own computation, and then it's the time to aggregate the results at the master. So now you use Mpi send and receive. So Mpi send, so that is shown in blue here. So I will explain each of those arguments in detail. So you have Mpi send. The first argument is the send buffer. So this is the local data that is computed. So the local data is something that is computed in D. So the variable D, or it's an array. So there you have the result. So that's the send buffer. How many elements of data is computed? So it is the count of sent items. What is the type of the data that is sent? And where are you sending it? To which process? So that is the process ID of the destination process. And what do you want to call this message? You can give specialized names, and that is the tag. So that is the message ID. And lastly, you have the Mpi com world, which I explained earlier. So that is the communicator or message group. So think of that as a WhatsApp groups, okay, but for processes. Okay, so now in Mpi Receive, so this happens in process 0. So note that you have if rank not equal to 0. All processes which are not having that rank 0, they execute that code. And one process that has rank 0 executes this code, which is Mpi Receive, which means that process 0 receives the results computed from all other processes. So the first argument there is the receive buffer, and that is the number of points that are expected. Then you have a special wildcard macro, so which tells, so it's a flag that tells that process 0 can expect a message from any other process. So the source of the message can be any. That's what it says. And then it can expect any message IDs. So that is any tag. So these are special flags that are there in Mpi. And then, so that's how you use Mpi send and receive. So now, the processes, they were explicitly sending and receiving messages amongst each other. So we call that as point-to-point communication. Now you can also have, instead of this explicit send and receive, just like in OpenMP example, you had reductions, you can have reductions in Mpi as well. And reductions is an example of what are called as collectives. So you can aggregate the result of the master with the help of a collective, with the help of a collective called Mpi Gather. And Mpi Gather, here, the first parameter is the receive buffer, num rows, or it's the send buffer if it is the non-master, and the count of the sent items, then the type of the data that is sent, then D is the receive buffer which exists at the master, num rows is the count of the receive, then the data type that is mentioned, and who is the one who is aggregating, who is the aggregator. So that is the source process ID. So Mpi Gather API expects all these parameters, and that's how, instead of send and receive, you could just have one line that does the same thing. So there are other, so pictorially, Mpi Gather works like this. So P0 is computing temp D, P1 is computing temp D, and there are two rows computed by P0 and P1. Now D is a memory block, created in the aggregator. And Mpi Gather basically gets these two rows which are computed by P0 and P1 and puts them in the block D. So I mentioned about this. Send receive are basically point to point. And in most Mpi programs, communication is between a pair of processes. And collective operations are costly. Collective operations, you have like broadcast, one process sending message to all other processes in the group. You have reductions, you have gathering of or aggregating data. You can also have scattering. So one process sending data to several. And then you have all-to-all communication as well. So depending upon when send and receive is complete, we can have different flavors of these communication APIs. So synchronous, asynchronous, blocking or non-blocking, or buffered. So I will not go into the details of what each of these terms mean. So they'll be handled in a separate session on Mpi programming. But a big picture of how these, so one synchronous versus asynchronous works is, so in synchronous, sender is notified when the message is received. And in asynchronous, sender only knows that the message is sent. If you think what is happening with this communication, so data is sent by the sender, so that, and it goes and sits in the buffer, network buffer. And then it travels across the network and goes and sits in the receiver buffer. And then the data goes to the receiver program space and becomes a copy there. Okay. So sender and receiver, they are different processes, each having their own copy of data. Now, you can or cannot have buffer. You can have limited buffer space. And so that is the buffered way of communicating. Then you can have sender waiting till receiver gets its own copy. So that is synchronous, or that is blocking. You can also have non-blocking. So that is blocking and non-blocking. So sender waits till the message is transmitted. That is till the buffer is, the send buffer is empty. And receiver waits until the message is received. And in non-blocking, sender continues the execution immediately after calling send. So what it means here in the previous slide, sender can call the send API and then continue executing the subsequent line without waiting for this yellow dot to be sent out of the buffer. Okay, so there are other collectives that are available in Mpi programming, and those are barrier, broadcast, scatter, gather, all gather, reduce, all reduce. And there's an excellent tutorial on Mpi at llnl.gov. Now, the performance of a parallel program, it depends on how much parallelism is there in an algorithm. And you can have different types of parallelism. So embarrassingly parallel programs versus sequential programs. So what is embarrassingly parallel? So that blue dots example that we saw earlier. So there we were supposed to compute distance between every pair of dots there, blue and red. And the workers, they did that without talking to anybody else. So actually computing the distances happened without talking to other worker threads. All they needed was 2 dots, and then they could compute the distance. So that is an example of embarrassingly parallel. There's no communication involved. And the performance also depends on granularity. So what is the size of the partition of data that is done when you divide this work among different processes? So you can have coarse or fine-grained. And then there's also locality that affects performance. Does the data that you divide, does it reside close to the place where it is used or not. So I mentioned this earlier. So every process has a copy of the variable A. If one process doesn't ever use it, then it doesn't need to have that copy located there. So locality is about that. And then you can have spatial versus temporal locality. Spatial means, temporal means it's if the data is used, then it is going to be used in the near future. Spatial means that if a data is used, it's the data that is located closely in space to the data might be used. So that is spatial locality. Okay, so how do we parallelize? First, we identify concurrency. Then we decide how to exploit this concurrency. So whether to have coarse-grained or fine-grained partitions. And we weigh the pros and cons of communication overhead versus creating more parallel work. Okay. So if we have coarser chunks of work, so if our blocks are bigger, then the communication might be less, but there might be lesser opportunities for parallelizing. If our division of work is finer, okay, so we might have to do more communication, but there are more opportunities for parallelizing. So that is a design decision. And then you have to divide the computation and form tasks. So this is a flow of how to translate from a sequential program to parallel program. So initially you have a sequential program. You break that problem into multiple tasks. And this is the decomposition step, problem decomposition. Now you have several tasks. You can have coarse-grained or fine-grained tasks. You assign these tasks to execution units. And what are these execution units? Threads or processes. So you have tasks assigned to different execution units. Now, if they don't ever communicate, then you have an embarrassingly parallel situation. But if they do communicate, then you may have to orchestrate the communication among different execution units. So in case of Mpi programming, you will have to set up the communication channels like send and receive, and you need to actually send the data. So once you have orchestrated the communication, you have set up communication channels, you need to map these execution units to processors. Because you have 4 cores or 4 processors here, P1, P2, P3, P4. Now you need to map these different execution units, threads or processes, which are running different tasks to these 4 cores. Let's say we have core P1, which is a fat core, and core P4, which is a very light core. And if T1 is doing floating point, if T1 is doing some floating point computation, which can be done very efficiently in the fat core P1, and you happen to map T1 to P4, then that is not the optimal way of doing things, and you might lose out on performance. So that's what I mean by mapping these execution units to different cores. So that is a pictorial view of how to go from a sequential program to a parallel program. So these 4 steps, decomposition, assignment, orchestrating communication, and map, so they might be handled by the programming model for you, some of these, not all. And in some models, you might have to explicitly do that. Some programming models, they might provide constructs, programming constructs to explicitly say decompose problem or assign it to different execution units and so on. So it depends on the different programming model that you use. So recap of programming models, you have single program, multiple data. So we saw something that was very similar. So you have OpenMP parallelism where a master thread. So master worker can be also thought of as master slave. You have one example that I think of is web server and web clients. This is about different programming models, and that's all I have for this theory session. And I would like to acknowledge various people. Firstly, NSM Nodal Center and the HPC Operations Committee, Dr. Rupesh, Dr. Unikrishnan, and these different sources. Thank you. So I'll now take any questions that you may have. And next, we will move on to the hands-on session. Over to you.
I had a quick question.
Yeah.
So is there a sort of a rule of thumb which says that, systems with GPUs would perform better than, say, distributed memory systems or something like that?
So these CPUs and distributed memory systems, they are created for different purposes. And they are good at doing things. So they're not good at doing, okay. I would say they can do specialized things. For example, you want to do vector processing. Okay, so GPUs are really good there. And in distributed systems with millions of cores, you might end up doing a lot of communication. So that's the thing. So I don't know, maybe Rupesh can add on to that.
Yeah, I mean, I agree with Dr. Nikhil that these are probably for different things. I would rather recommend that you combine both of them. Have a distributed setup, having nodes, having shared memory as well as GPUs in them, and use this heterogeneous system to get. So I think there is no as such rule of thumb. It totally depends upon how the locality and parallelism within the code is.
Dr. Nikhil? Hello?
Yes.
Yeah.
Yes.
So, may I know, like, this could be a very basic question, but still I would like to know. So how do you, like you said that thread will see itself as like the entire processor. So if I have a desktop computer with 4 CPUs, how should we understand? Like, should I say that I have 4 threads only? I do understand that there are 4 cores, but how should I see the threads here?
Okay. So if you have 4 cores, now you can run a program with 4 threads, or you can have 4 processes, each with 1 thread.
Oh, 4 processes with each with 1. Okay, 4 processes means like 4 separate jobs I should see. Is that correct?
Yes. Yes.
Okay, and how does this hyper-threading comes into play? Like, where does this hyper-threading is useful, and how should we use it if the core has hyper-threading?
So if the core has hyper-threading, then the programmer, it is something that is exposed by the hardware to the operating system. So programmer will have no way of controlling that. So all programmers, so that is an illusion given to the programmer that there exists double the number of cores.
Okay, okay. Okay, so when we, if we have hyper-threading for a 4-core CPU, then when you give the command like OMP num threads or something, then it should give us 8 instead of 4. Is that correct?
Yes, yes, yes.
Okay, fine. Thank you. Yeah, that's all the major question.
Yeah.
Can we combine OpenMP as well as MPI in a single program?
Yes, you can. So you can have hybrid programming models, so where you can combine both OpenMP and MPI.
Okay. And in distributed memory implementation, can we have unbalanced distribution of work? The example that we saw distributed it evenly across the other processors based on the availability of the processors. Can we unbalance it?
Right. So you might not want to unbalance it intentionally, but that happens all the time. So when you don't know statically upfront that how much work is going to come, you end up with a load imbalance.
Can I use a ping or a standard program running on other processors to figure out how busy they are and then distribute the work?
I didn't get that question. So can I use what?
Yeah, suppose I have four machines which are connected in a distributed way. Okay.
Okay.
So
okay.
Out of the three processors, two may be busy and one may be slightly busy, and the fourth one is distributing the processors across the three. So if the second one is busy, I'll send less amount of work to that. And
yes. Yes. So in the master, we have in the master worker model. So these kind of things can be implemented. So these are typically implemented as master worker model.
Okay, fine. Thank you.
So the master pings the worker to check how busy the worker is, and then assigns work based on that.
Any further questions, either on the current session or the earlier session?
Nikhil sir, regarding distributed memory system, at slide number 117, I think you have mentioned programmer must decide where to put the data. So I couldn't capture the meaning of that aspect. Yeah.
Okay.
So in this distributed memory programming, so data will be present in separately in each processors. So ultimately, it will be combined in the master processor, is it?
Not necessary all the time. So if you decide to divide your work in such a way that there is no one master worker that aggregates all the results, all the workers, they do their own stuff and then they complete it and let's say write it to a file. Okay. Then they're not talking at any point in time with each other. So that is, you can choose to do that. So, and what I mean by this programmer must decide where to place data is that, so each process is operating on some data. And if a process does not get the data that it wants, then what it has to do, it has to send a message to another process that has the data. Right? And if it happens that all the time the process is sending messages to other processes to fetch data, then that is not a good division, or that is not a good assignment of data to processes. So in that sense, a programmer should assign data to processes in a way that it is used at that process. So that's what I mean. I hope I answered that question.
Yes, sir. Yeah. Sir, other thing, so it's a clarification only. So
Yeah.
you have mentioned embarrassingly parallel. So in a way,
Yes.
actually it's advantages, right? So some of the processes will be much advanced in doing certain set of instructions, and other let it be slow, but ultimately we get the quicker calculations. So why should it be called as an embarrassingly parallel?
So some problems, they fall into that category. So that's why, I mean, that phrase was coined, I don't know who coined it, but so some problems that have that pattern of computation where there is no communication involved, they're called as embarrassingly parallel.
Okay.
So that's a category of parallel programs.
Okay. Yeah. Another one. So in a set of, for a given set of instructions, suppose for the third instruction, that information from second instruction is required. So
Okay.
will the processes which are in parallel will wait for the earlier instruction to come in, or how that happens when there is requirement of previous instruction for the current one?
Yeah, so if there are data dependencies, then the programmer must make sure that those data dependencies are respected. Okay. So if the programmer assigns third instruction to processor P3 and second instruction to processor P2 and first instruction to processor P1, then all those instructions can be executed simultaneously by each of those processors, right? So in that case, you are not respecting data dependencies. So if you want to respect those dependencies, then you must explicitly say to processor P3 that wait till P1 and P2 are done with their computation.
Okay. Yes, sir. Thanks.
Okay, thanks.
If there are no further questions, we'll take a break of around 10-12 minutes, and we'll meet again here itself at 3:30.
All right, so I'll be back at 3:20.
Sure. I'll leave the session open for everyone.
Okay.
Everybody can be logged in. Thanks.
I'm here, Rupesh.
Sure. We can get started whenever you are ready.
I'm ready.
Sure.
When okay, this is in response to an answer, in response to a question that Amit asked. So can I alter the resources of running jobs on PBS? While the jobs are running, you cannot change anything. But if the jobs are in queue, you can use queue alter. So you change the resources. But you cannot change the exact commands, but you can still change the resources. Okay, welcome back. So in this hands-on session, you'll be working on the two problems. One is on parallelizing computing the value of pi using OMP, and the other one is parallelizing the computing the value of pi using MPI. So in the first OMP programming exercise, you are given a sequential program, pi_sequence.cpp. So you have to stick in hash pragma directives to make it parallel program. It's a parallel OMP program. You have to compile it, and then you have to write a job script to run it on the cluster with different number of threads. So this problem asks you to create different jobs with 1, 2, 4, 8, 16, 32, and 64 threads. All these jobs must run on one node. Now, the problem also asks you to observe the speed up or runtime compared to one thread run when you run with different number of threads. And in the second problem, you'll be doing the same thing. So it's the same program, but you'll be using Mpi programming model. So you have to use reductions in Mpi to implement computing the value of pi. So for this, you have been given a program pi_mpi.cpp, and some of the lines in this program are removed. So you have to fill in those lines to complete it and compile it and run it. Now the commands that are shown here, they might not work in your cluster environment. In your cluster, you might have Intel MPI, so you'll use MPI IMPI, so our Intel compiler toolchain. So, and once you are done implementing this and compiling this, you'll get an executable pi_mpi. So to run this MPI program, you'll use MPI run. So as you actually saw in the morning session, hands-on session, that Mpi run can launch multiple copies of an executable. And we saw host name as an example. So in this case, we will be using Pi_Mpi as the executable to launch. Okay, so if you use Mpi run minus np10, it will launch 10 copies of the executable Pi_Mpi. Okay. But you should not execute this command on the master node. And the reason is that, like, you know it. Master node should not be used to execute a program. It should be used only to compile, do lightweight tasks. So all your computation must happen on the compute nodes. And in order to do that, you have to create job scripts. And for this exercise, you have to create jobs that run with these processes 1, 2, 4, 8, 16, 32, 64. And all these processes must run on one node. Okay. So I haven't asked you to request for more nodes because you might end up waiting for a long time in the queue. Your job might end up waiting a long time in the queue. But still, this is a worthwhile experiment to see the performance when you look at threads and processes implementation. And specifically about Riemann sums approach. So you have x square plus y square is equal to r square. This is the formula equation of a circle. And if you consider a unit circle of radius 1, okay, you have x square plus y square is equal to 1. And y square is equal to 1 minus x square. Y is equal to square root of 1 minus x square. So y or f of x is basically square root of 1 minus x square. Now, if you take a quarter circle, then take only the positive, the first quadrant, which falls in from x is equal to 0 to 1, okay, and positive values of y, then that is one quarter circle. So in Riemann sums approach, you break this quarter circle into multiple small rectangles, and you find the area under curve by summing the area of the rectangle. And this equation here, so sigma I equal to 0 to n minus 1 delta x f of xy, is basically computing the area of a rectangle, and you are summing various smaller rectangles. So if you look at delta x is 1 by n, and n is the number of chunks that you have decided to chunk up this quarter circle. So delta x is the width, and I delta x is the x coordinate of that rectangular chunk, and f of xi is basically, it gives you the y value or height of that rectangle. So you are computing width into height in this formula, delta x into f of xi. So that is the area of the rectangle. So, and you are summing up all the areas. The final sum is basically the area of a quarter circle. And so if you want to find out the value of pi, you should divide that, you should multiply that sum with 4. And then you'll get the value. So that is the like theory behind this program. And yeah, so you can get started with your Mpi and the OpenMP programs. Yes, I saw a question. Yeah, you need to include a header #include empty.h. So in response to the question that SY asked, so you're missing one piece of code element there. So each of those worker threads, they do their computation and they're writing to that shared variable. And there is a race condition there. So you have to do something about it. And the problem statement asks you to use reductions. So that's one other hint. Okay, how do we specify the number of processes in the program here, or is it automatically taken care of by setting the number of Mpi threads variable? Okay, so whatever you specify in PBS script or Slurm script, that is the resource that you are requesting. Okay, so that is the hardware number of cores that you are requesting. And so now your OMP program will have an illusion that it is running on a computer with that many number of cores. Okay. Now you have a computer with that many number of cores. You can choose to decide, you can choose to create as many threads as you want. You can create 128 threads and run it on your 8-core machine, right? So in the same way, you can, so those are two independent things, requesting the number of cores in PBS script and running with a specified number of threads in your OMP program. I hope that answers your question.
Hello, sir.
Yes.
Sir, do we need to take this file to home directory before compiling it, or we can do it directly from the scratch?
Which file?
This file dot file
Pi underscore
pi
OMP or pi
underscore
underscore
OMP dot cpp, sir.
pi underscore
After
MPI dot CPP?
That
Yes.
we need to compile it, right, sir?
Yeah, so you need to fill in the blanks in that pi underscore MPI dot CPP and then compile.
Okay. That compilation we can do in scratch folder itself. Right?
Yes, yes.
Okay, sir. Okay. Thank you, sir.
Yeah, so it doesn't matter in which folder you are in.
Okay.
Yeah.
If you are doing it in terminal, it means it is in master, not.
Yes, yes.
Okay. Sorry. Thank you.
Yeah, thanks.
Hello, sir.
Yes.
Sir, what is the executable command?
So if you have an executable pi_omp, if you do /pi_omp, it will be run. But where do you do that? Where do you run your /omp command? On the compute node, right? So which means that you have to insert that in a job script.
Okay. Okay, sir.
So that compiling part need not go in the job script. G++, that command need not go into the job script. That can be done on the master node itself.
Okay. Okay, sir.
Yeah. So this, because like compiling takes a lot less time, and you want to know if there are any compiler errors. You don't want to wait a lot of time in the queue, then the compute node tell you that there are some compiler errors. So that's why a reasonable way of doing that is doing it on the master node.
Okay, sir. Thank you.
There is one question from SY. How do we invoke the command omp get num procs? So the correct way, so it is not exactly a command, it is a function call or an API provided by OMP. So you, OMP get num procs returns the number of processors available on the system. So if it returns something, you should capture that and store it in a variable. So you do something like this, and that it will be an integer variable that is returned. So int num procs is equal to NP followed by semicolon. And then you just print the num procs. So
Is your screen visible? I can't see it.
I'm not sharing anything.
Okay, sir. Sure. Okay.
Hello, sir.
Yes.
Sir, I tried to compile, but it's showing compilation terminated. Means, and one more that include vector.h. This not took actually.
Okay. So what command did you use to compile?
That g++ space that f open mp pi dot that's
Okay.
input file.
Got it.
Yes.
You're saying there is something to do. It gave a compiler error with respect to
Yes,
some
means
the vector.
is showing fatal error vector.h.
Okay. Can you paste the exact compiler error?
Okay, I paste. Okay.
Yeah, so can I say something?
Yes, please.
Yeah, see, I ran the program with OpenMP, and it looks like irrespective of whether I use 2 or 4, 16, 32, I'm getting the same speed up. You know, the serial code in comparison to the serial code that you gave, it is giving 30 times faster code. but irrespective of the number of threads that I'm using, that is the result I'm seeing.
Okay. So I'm just thinking why. What thing? So where to start? So are you using OMP set num threads?
Yeah, I'm using that. So I changed it all the way from 2 to 32. That is the maximum I can do on my system. Okay, and because it's a 40-core system. So, and now, so irrespective of whether I use 2 or 32, I'm getting the same runtime. Okay. And, but it is much faster than the serial code. I ran the serial code that you gave without any modification. In comparison to that, it is running 30 times faster. But but the number of cores, the number of threads is not having an influence on the speed.
Okay.
What I'm seeing, yeah.
Okay. So I'm not able to figure out what could be wrong there. So one, that superlinear speed up, which means that, so if the runtime was 30 seconds, and with two threads, if the runtime came down to 2 seconds, then you have like 15x speed up. Okay, so that is superlinear. So that still should not be so huge when moving from one thread to two threads. And you said like there is no performance difference when you use 2 threads or 32 threads. So what?
That's what I'm seeing. Yeah, I'm not sure.
How much was the runtime with sequential run?
Sequential. Okay, see, I'm not using this. I'm not submitting as jobs because this is my own cluster and there are no other users. So I'm just running it as just on the terminal, and I'm using the time command to time the code. Okay, and the serial code the ran in let me just check. 15 seconds, I think. Just always. So let me check. Hold on. Yeah, the serial code ran in 15 seconds, and the OpenMP code, irrespective of number of threads, is running in 0.5 seconds.
Okay, OpenMP code with how many threads? Like 2 threads onwards?
Irrespective number of threads, is running in 0.5 seconds.
Okay, so that.
So which is a 30 times speed up, irrespective of number of threads.
Yes. Okay, so I don't know what is happening there. OMP set num threads. You say
using that. I'm using that to change from 2 to all the way to 32.
Okay.
Yeah.
Rupesh, any inputs?
Yeah, I was just wondering if the output is turning out to be exactly the same, or is there any difference?
Output is the same. Yeah, it is the same. Getting the correct value pi.
I think we'll have to take a look at the code. And
Shall I copy paste the code?
Yeah, either that, or you could put it on a drive and share the link. Either way is okay. Or you could share the screen if Nikhil is okay with that.
Yeah, I'm fine. You can share the screen and let's try to.
I'm not able to share the screen. That option is not open to me.
Let me try making you present. Could you please try now?
No, I'm still not seeing that.
Oh, yeah, then the only option I see is, I mean, if you could share the code somehow, we'll be able to take it.
I'll paste into the
Sure.
the chat box.
Just to add to the discussion, ideally we should not get 30 times speed up with 2 threads. Somewhere I think what's happening is, I mean, this is my guess, is that it's using maybe 32 threads for all the values, and therefore we are getting exactly the same output. I mean, exactly the same performance. And that's why the performance improvement is also 30x or so.
Yeah, but I'm changing that variable. Let me just check once more.
Yeah.
So I pasted the code in the chat window. If you can check it out.
Yeah, that's.
So Ranjit, in this code, I don't see any OMP underscore set underscore num underscore threads call. So this code would run with all the cores that are available.
Oh, okay. ONP, say that again. What is that thing that I should set?
OMP underscore set underscore num underscore threads like root. So
No, that is an environment variable. No, I set that outside, right? I'm changing that outside.
Okay. So if you set that outside, that environment variable should be available at a place where your job is run.
Yeah, it is. Yeah, it is in my same. It is in my So in my dot rc file, no, dot rc file, I have a command exclude export OMP underscore NUM underscore threads equal to 2.
Okay.
I have set it that way.
Okay. And you do every time you change the run, you do source of that RC file?
Oh, I think I missed that. Okay. Yeah. I think, yeah. Yeah, I think then I think it's running with 32 all the time. Yeah. Let me just quickly run it with 2 and then we'll see.
Okay.
Yeah, now it's looking correct. So now 2 threads is giving me 7 seconds. Okay, so yeah.
Great. Thanks for that.
Linear scaling, yeah. So if I want to use this set OMP set num threads in the code itself, where should I include that command? Right in the it can be included anywhere in the code, or it should be the header or what?
So it should be included just before where your hash pragma OMP starts. The first hash pragma OMP before that.
Okay.
Or it can even be like the first line after your main starts.
Okay. I'm not able to use that that command OMP set num thread. It's giving me error when I use that in the code itself.
What is the error that you see?
The error is OMP set num threads was not declared in this scope.
Okay, so I think you are missing that hash include omp.h
Oh, okay, that has to be
in the first line. Okay, so maybe I'll start explaining the solution, and let's start with OpenMP. So I'm trying to share my screen. So the font big enough. Is my screen visible?
Sir,
Yes.
Okay. Great.
yeah,
So I have
it's coming up.
I have pi_seq.cpp. This is the sequential version of the file. I'll use a different editor. So now I need to make an OpenMP program out of this. So the first line, I will add hash include omp.h. So this is hash include omp.h. And now what is happening here is that, so this is exactly, there is a one-to-one correspondence between the naming of the variables and the equation that is shared in the problem statement. So you have delta x, you have n, and you have pi. So the value that of pi that is computed here in this sequential program it's done after accumulating the result of computing the area of those smaller rectangles. And if you want to parallelize this, then you can give computing the sum of a smaller subset of these rectangles to one worker and another subset to a different worker and so on. So this for loop has n iterations or n rectangles to be summed. So you have to divide the work among now, say, let's say p workers. Okay. So now you don't have to do any n divided p by p or something like that. OMP takes care of this automatically for you. All you have to do is add the first hash pragma OMP directive. So hash pragma OMP parallel. So this is the first directive, and here hash pragma. Okay, so when I say hash pragma OMP parallel in this line, a set of workers are created. Now those workers, they need some work, and that work is happening in this for loop body. I need to divide this for loop body into multiple chunks so that those workers have some work to do. Okay, so for that I can do hash pragma OMP for. Okay, so this I can do, and the work is divided among multiple threads. Now, one problem with this code is that each worker will be updating this value of pi, so there is a data race. And to avoid the data race, there are multiple options. Now, if I use reduction, so this is the syntax. Make sure that you have the syntax correct. So plus followed by colon and total, or pi in exactly. I save, I exit, and now I have to create a batch job. Okay, so first let me rename that file. Mpi_seq.cpp as mpi_omp.cpp. So now next I need to compile this, and the command for compiling is g++ -f openmp. So this is the flag that you specify to the G++ compiler to tell that this is an OpenMP program. And next, you give the name of that OpenMP file, omp.cpp. And next, you write the output, which is an executable, in a file called pi_omp. Now you have an executable called pi_omp. Now, should I do this or not? Any volunteers?
No.
No, very good.
We try to.
So, yeah, thanks for those answers. So I'm on master mode. I should not be executing. I need to write a batch script, and I have one batch script here already written. So Vim. So this batch script requests 32 cores on one node, and I'm just doing /pi_omp. So now as batch pi_omp_32.job. So and now I can say so I see the correct value of pi. If I want to time the value of pi, then I need to speak the time command. So here I need to type time followed by this. And now if I do as batch, I have this. It's not, the result is not very hard. So the result is there, and it took about 12 seconds. Okay, so 12 seconds with those 32 cores, which seems something, it seems strange. So it should not be so high. So 12 seconds to compute pi with 32 cores. So there is something that I have to do some work there. So
no, in the code, you didn't set the number of threads in the code, I think.
So I don't need to. That is the beauty about OMP program. So here, right? So the programmer is oblivious of the number of cores that are available. Okay. So in my program, I don't need to set the number of cores, but so there is some problem which with the cluster. So, but if I do the same thing on my local 6-core laptop, it works fine. But if I do this set num threads 32 and sorry about that. And now if I do s batch I underscore I can just take it. So I'm requesting 32 cores and I'm timing Mpi_omp. So now back, so with 32 cores, I can get in 2.8 seconds, I can finish the computation. So this is expected. So with one core, I had about 15 seconds. And then with these 32 cores, so 2 seconds. So the real is the wall clock time. User and CPU is user is how much time is spent in user code, and sys is how much time is spent in the kernel code on the CPU, how much time is spent executing the kernel code. All right, any questions before we move on? So if you do this for different, so n tasks per node, if you request different number of cores here, and if you keep your OMP program same, then you should be able to, so if you make this 2, instead of 32, if this is 2, and run your OMP program, it is as good as running your program on a dual core processor. So, that should, as Anurag pointed out, on the cluster, he's seeing a linear speed up to 16 cores. All right. So next, let's move on to the MPI part. So any questions before we move on to MPI part?
This will only run on one node, right? Or we can use any.
Yes. So good question. So OMP program, it runs only on one. So it's a shared memory program, right? So it will run on one. When you're using MPI programs, you can use more than one nodes there. And as someone asked, so you can have a hybrid program which with MPI and OpenMP. Okay. So let me open Mpi_MPI.cpp. Okay, so in this code, you're asked to fill in these two lines. So as indicated by 2. So this code implements the same program that you did in OpenMP, computes the value of pi. So first, in an MPI program, you have to have the initialization sequence, and that's why you have Mpi init. So once you're done with Mpi init, now you want to know, if you want to know what is the process ID, how many processes are running, then you have to use these variables rank and size and pass those variables as arguments to Mpi com rank and Mpi size. Mpi com world is the default communicator. So the group of processes that communicate with each other. And next you have the for loop. That is
Dr. Nikhil, can you just tell what is argc and argv? You mentioned, but at the time I had the disconnectivity of your video.
Sure. argc and argv. So think of that those as names which are given to some memory locations. So any variable is a name given to some memory location, memory address. And ampersand here, which is prefixed before argc and argv, ampersand is called the address of operator. So you are fetching the address of that memory location.
Okay.
So Mpi init, you are passing the address of that memory location, and Mpi init expects the address rather than the value present at that address.
Okay, so this is the memory address, that's all, not the value that is there in that memory.
Exactly.
Okay. So is there any difference between argc and argv here? What do they represent? Just that's a memory address, that's all.
So if you look at argc here, they are the parameters of the function main. Okay. So argc tells you the count of the number of arguments passed to your executable.
Okay.
And argv is the string representing each of those arguments.
Okay. So number of arguments and what are those arguments? That's what it
exactly. Right,
okay.
Right.
Okay. Thank you so much.
These are the command line parameters.
Yes, exactly. So if you were to do /a.out hello, then your argc will be 2 and argv of 0 will be /a.out and argv of 1 will be hello.
Thank you.
Yeah. Okay. So now, what is the code that we need to fill in here? So it is if it is the one-line code, then it will be Mpi_reduce. So let me open the solution that I've already prepared. Okay, before I move into, I go about filling in the details of this. So this is easy. So in the end, you have to call the termination sequence. And termination sequence is nothing but calling Mpi underscore finalize. So should not be forgotten. In any Mpi program, this must be done. So Mpi init and Mpi finalize. So I'm just opening up that slide. Okay. So slide 121, you have the details. And now slide 132 lists all the collectives. And now we are using Mpi reduce. It is equivalent to the reduction that we did in OMP. So let me just pull up the solution. Can you see my screen?
Yes.
Okay. So this is that first to do. Mpi reduce. And the first argument to Mpi reduce is I should specify the address of this buffer or receive buffer. And what is the receive? Where should I receive the data? That is in a variable called sum. And next, this is ampersand pi. So from where I should receive? And how many bytes to receive, and what is the type? And what is the name? So what is the reduction operator needs to be applied? Mpi sum. And who is the one who is the aggregator or collecting the results of all the reduce? And lastly, the group. So this is Mpi underscore sum is similar to that in OMP where you had plus followed by a colon. Right? So exactly similar to them. So this line basically gathers the value of these pi computed as partial sums in different processes. So as you can see, these variables pi, sum, they are all available as copies to all the processes. So single program, multiple data. So even though they are available as copies to all the processes, the value of pi is correctly computed only in process 0. Because process 0 is the one who is aggregating the result as indicated in Mpi reduce as in the in the sixth parameter, 0 here. So now if rank is 0, which means if the process 0 is executing this code, then it is in a position to correctly print the value of pi which it has received. And this code in addition has this lines to measure the time. So this is not mentioned in the code that I shared with you. But yeah, this basically, instead of time, I'm doing this within the code.
So Dr.
Yeah.
Yeah. So how do we know these arguments a priori? Like you are saying us that, okay, I need to keep this $ampersand sum, ampersand pi. What do they correspond to? You are saying. So how do we know what do they correspond to?
Sorry, I didn't. So you need to look up the API specification of each of those functions calls provided by Mpi.
Okay. So that will be in some web page or something?
Yes. So Mpi standards, so there are nice tutorials, and also Mpi standards page, they have all the specifications for each of those API. So just like this for OpenMP, I have openmp.org and I have all these function calls. You have something similar for Mpi as well.
Okay. 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 And how are you deciding that 1 byte? There you mentioned that 1 is for 1 byte, if I heard you correctly.
So not 1 byte, one data element of type double.
Okay.
And double, it depends. Sometimes on some machines, the size of double is 8, and on some machines it is 4. So it depends.
Okay. Thanks.
Dr. Nikhil, I just had one question not regarding this. So
Yes,
in this, so in case of MPI, just
yeah.
like we have for say serial programs, we have a debugger type where we can see the runtime values of the variables. Can we?
Yes.
Is there something there for MPI also?
Yes. So you can use GDB. If you have written a C++ program, you can use GDB to open up multiple GDB windows and start debugging.
There is no single type, means you have to launch all of them. What different? So how does that work? In case of serial, we have only one, and we just see on the.
Right. So let me just try to show you. Okay. So if I have okay, the first thing, if you want to debug, you need to add the debug symbols. So G++ minus G by underscore OMP.cpp minus O by underscore O. So let me go with this. Okay. So now I use GDB pi underscore C. And it gives me this terminal. This is the normal way of working with GDB. Now, if I have an MPI program, you would do MPI run minus MP like 2, followed by pi underscore C. So this will launch 2 copies. I hope you are able to see my screen.
Yes.
Okay. So this will launch 2 copies of pi underscore C, the program pi underscore sequence. Okay. So now, how do I debug this code? So I can use Mpi run minus mp2 cpp e extra for okay extra and pi sequence. Oops. Okay. So on my Ubuntu WSL, that X server is not running, so I'm not able to get 2 windows. So, but this is the command. So you launch GDB as 2 processes and pass that minus E external followed by the executable name. So this will give you 2 GDB terminals. Okay. And you can start putting breakpoints in your program code and switch back and forth between one GDB terminal to another.
Okay, thank you.
This is interesting. So, Nikhil, this opens GDB on 2 different nodes, is it?
On the same node, but you have 2 different terminals.
Oh, I see.
Yeah. So if you want to do it on 2 different nodes, then you need to run the code in interactive mode. And I didn't cover interactive mode in the morning session.
Right. I see. Okay. Sure. All right. So we are over time, but if there are any questions, we can take those up.
Regarding this GDB only in case of MPI then. So is there,
Yes.
for example, there is a IDE, say Eclipse type integration of
Yes.
GDB with that. So it is easier to see. Is there any IDE that will do this also? Or do you have?
I'm not aware of any GUI-based debuggers for parallel programs, but there are these profilers which are GUI-based.
Okay.
All right. If there are no further questions, we come to the close of day 1 of this NSM HPC workshop, and I'm very thankful to Dr. Nikhil for guiding us through various aspects of submitting jobs to the cluster, and then the second part of parallel programming, and evaluating various aspects of, let's say, OpenMP as well as Mpi program. And I think the problem statement chosen was very interesting, quite crisp, and those of you who could get it must have enjoyed it a lot. And if your hunger is still there, next week on the same day we are going to have further session on the parallel programming. We'll touch upon a few aspects of OpenMP and Mpi a little bit initially, but primarily it is going to be on Mpi on GPUs. So I would like to also thank all of you for staying through. It must have been a hectic day for not only Nikhil but also all of you. But I'm sure it would be worth it. So with that, we come to a close. Anybody wants to say anything?
Yeah, thank you, Dr. Rupesh, for this opportunity. I enjoyed this workshop, and also thank you all the participants for those wonderful questions. It's a great experience.
All right. So thanks a lot, everybody. Have a good weekend, the remaining part of the weekend, I would say. And we meet next Saturday. Bye.
Bye.